Okay, so in this lecture, we will continue our discussion on the I/O management by the operating system. So in the last class, I introduced you to the concept of devices, how devices are connected to the system, and how does the OS play a role in ensuring that the I/O is interfaced to the system and how the data that moves between the CPU and I/O is managed. Okay, so let us quickly recap the concepts that we covered in the last class, and then we shall move forward. Well, so in this module, we are talking about the concept of I/O management. Okay, so what is the idea that we discussed yesterday is the basic job of a computer, as we know, is to do computation. So a computer is supposed to do some kind of computation, and in doing so, it requires some processing element which we call the CPU and a storage element which we call the memory. So these are the two components that are usually used for performing any computation. The data is stored in the memory and they are accessed by the CPU and processed accordingly. Well, this is the first job or the primary job of the computer. In addition to that, the computer also performs some kind of data movement. And as you see that there are a lot of, the computation requires data, and data is normally provided through some external devices, which we often call the input and the output devices. So input devices are supposed to provide the data to the computer system, and the results that are generated, again, in the form of some data, is provided to some output unit for display purpose or for storage. So there is a lot of data movement that goes on. And this data movement is taking place between the input and the devices and the memory. So this is the second job of a computer system, to ensure data movement. It requires data to be read in, and then finally the data that is generated will be stored or displayed. Well, the problem, this is fine. This is what the computer is supposed to do. But the problem or the challenge that is faced is the variety of devices that are connected. So the data that you obtain or the computer obtains is from different kind of devices. Every device has its own way of working, its own way of providing the data, and that complicates this thing. Because there are so many kind of devices and each device works in its own way, providing different kinds of data, it is essential that there must be some kind of a common interface. Because if that is not so, then every device will have its own way of working. And think about a situation where you put all those contents of all the devices within the operating system. And if any one of the device starts malfunctioning, that would create trouble for the entire kernel or entire operating system, and the OS may crash. So this is what we don't want. So the challenge is that there must be a variety of devices. Okay, you have to allow different kind of devices, but the goal is to provide a standard interface for all kinds of devices. This is the aim of the operating system. So whatever input devices are connected to your computer system, it does not matter. The operating system should ensure that all the devices that are connected are accessed by the OS or by the application through a common interface. It means you should not have separate ways of accessing them. There must be a common way of accessing all the different kind of devices. That's again takes us back to the concept of abstraction. If you remember, whenever or when I started discussing about the goal of an operating system, I always tried to impress upon that the basic goal of an OS is to provide abstraction of different resources, be it the processor, be it the memory, and here we see it also provides an abstraction of the input-output devices even. So whatever be the input-output device that gets connected to your computer, when that particular device is accessed by what? Accessed by a program, an application, or an operating system, it has to be through a common interface. We know how applications access things using or making use of an operating system. They do by using something called system calls. So even input output devices that are connected should also be accessed through the same mechanism. You should not have separate techniques for each of those input output devices. So this is the primary goal of an operating system. It should provide a standard interface or a generic consistent to access IO. Understand this very clearly. This is the goal of an. And most importantly, it should be device independent. Whether you are connecting an USB drive, or you are connecting a camcorder, or you are connecting some kind of a printer, whatever the device you have connected, the way to access that should be same for all of them, and it should not depend on the device specifications. And you should also have a very high performing. So you should also keep in mind that the access should be as fast as possible, because devices normally are electromechanical devices, whereas the computer system is a semiconductor device that works much faster as compared to the IO devices. Fine, so this is what we understood. We see that the different kind of devices that get connected to your computer system can broadly be classified into three categories. Block devices, where you access the data in form of blocks. The network devices, where you access data using packets. Packets are independent units of the data. You divide the data into small chunks and you send them one by one. Or you may have small level of data transfer, which is of the order of, let's say, 1 byte, we call the character level devices. The different, commonly used input output interfaces that we connect, whether it is a mouse or a keyboard or an audio scanner or whatever, these are all character level devices. So here itself, you see there are three kinds of devices. So all these devices, they get connected to the CPU, and all of them have to be accessed. Now you cannot have a separate access mechanism for different devices, right? There must be a very generic way of accessing them. So I'll show you what exactly is the mechanism for doing that. And the way that OS provides the interface is, one of the examples that we saw yesterday is how Unix provides this interface. And it treats the devices very similar to files. Let me give you an example that will make things clear. We saw that yesterday, but I thought that let me impress upon this by providing you an example. So let's say I write a code which is something like, say, fd equal to, or say I make use of a function called fopen, and we have something like, say, some device, and which is open in a read-write mode. I hope all of you remember this particular system call. It's a library call that tries to open a file, right? And we call this as file open. So what we pass to this system call is a string, which normally for a file happens to be the name of the file. But in this case, it's the device that we are trying to access. And that's, look at this idea. The device here is being treated as if like a file. Okay. So the same interface that you make use of for a file, it's the same thing that is used for a device. Okay. And interestingly, this particular interface is applicable for any device that you are going to access, the same interface. So you make use of the same system calls, open, pass the name of the file, which in this case is a device, and mention the mode in which you would like to access. In this case, it's read write. So I would like to read something from the device, and I would also be like to write to the device. Okay. So very similar to how a file gets opened, it returns a file descriptor, and then we use some mechanism. Let's say int I equal to 0, I less than 10, I plus plus, and what do I do here is I say want to print something what to the file which is defined by or indexed by this file descriptor, some value of, let's say, count. Okay, so you see that's a very simple interface, and it's very it's the same way that we access a file. And interestingly, this code works for many devices, because we are not mentioning any specific specific to a particular device. We are using an interface that is common across all devices. This is the goal of an operating system, to provide a standard interface so that you don't restrict yourself to the details of any particular device. Okay. Now, how does this happen is what we have been discussing in the last class. Okay, so what is this role of this particular code? The role of this particular code is to control a device. This is the basic. And you may also call this as a device driver. Okay, and it makes use of a standard interface. So this is what we discussed in the last class. Well, coming back to the different type of devices. So we studied, or we mentioned that every device will be treated, or the OS will provide an interface independent of that. So as we just saw, if you are handling block level devices will be treated like files. So all the functions that you have been using for files, like open, read, write, all these kind of functions will equally be applicable for block level devices. And we'll see that when we are going to write programs for accessing blocks from a hard disk, we're going to make use of the same kind of functions. Okay. When you talk about network devices, which talks or which moves data in the form of packets, we use standard interfaces such as sockets, where there are some defined rules, we call them protocols, that must be followed while the data transfer for the data transfer to take place. And when we talk about character level devices, we also come across different interfaces like get, put. We already are aware of these kind of functions which are used for handling character level transfers. So you see, the interface is the very common interface that we have been working so far while handling files. So the OS ensures us that we are not using any additional or any specific thing for a particular device. We are using the same interface that we are already aware of or we have been using. How does OS do that? That's what we need to talk about. But first, if we have already discussed about, we know that there are these kind of devices, let us quickly look at structure of one such device, because that will give us an idea. What is the challenge? How does the data get stored in these devices? And how will the OS ensure that that particular data which is located in this device can be accessed? Okay, so this is what we should know. So let us quickly move towards one of the block level device and let's see the structure of that device. This is where we left in the last class, and I shall start from here. I hope all of you are aware of the device which is called the magnetic disk, or we usually commonly call it the hard disk. Right? So this is the picture that shows the hard disk. Okay, let me simplify that further so that it becomes easier for you to understand. Okay. Is the picture visible to all of you? Yes. So this is the hard disk, which is a permanent storage that stores your data in the form of magnetic dots, and we call them block level devices. What are these block level devices? Let me draw this diagram in a more easier way. Now, if you can think this to be a disk which is of some material. All of you have been using the compact disc, the DVD drive, the CD drives. I think all of you have seen that. Well, so this is a disk which is having some kind of a material which is the disk is coated with a particular material that can store some magnetic dots. Okay, so this is the disk. Now, interestingly, this disk has a number of concentric circles. Okay, they have a concentric circles, and these concentric circles are called tracks. So it may not be visible here in the diagram that is shown, but you see the ones that has been shown in this as a brown, you may say that this is the the tracks which are there. So there are concentric circles and these are called tracks. Well, these tracks are divided into number of sectors, right? They are divided into number of sectors. So this is called a sector. Okay. And the data that you store is within this. So there are magnetic dots that are stored within the sector. So this is sector 0, sector 1, sector 2 in this way. This is what happens. This is one single disk. Now let me draw this in a lateral way. So there, this is the disk, and here is your tracks. Now this disk can have one-sided, there is only one side that will hold the data, or it can be two-sided. That means you can have data. I'm writing it in this way, drawing it here. So you can have the tracks and the sectors on one side of this disk. It can also be on the other side. Okay. So depending on that, whether you said it's a single-sided disk or a two-sided disk, whatever. Now, how do you read the data from this disk? There is something called a spindle, right? So here you have a wire or some kind of a rod that goes through. We call it a spindle, and there are not one but many disks which rest on that spindle. So it's like this. So here you see I have drawn 4 such disks which are in this way, right? Each one is having some sectors and tracks. So this is how they are arranged. So they are stacked one by one on the spindle. All of them, all these 4 can be one-sided disk, that is, the data resides on one side of the disk, or it can be two-sided. Okay. Now, how is the data read? Well, here is something called the reading arm. Okay. So let me call this as, this is called the disk arm. See, this is the diagram that is shown. This is the disk arm. So this disk arm is going to touch one of the sectors, and this disk arm has many heads. So it can be, we will call this as the head of the arm. So the head will touch a particular sector, and the sector to which that particular head touches, the data is read. So the data, the one that is touched, will be read via this. Okay. So this is how the heads will be touching. right? Okay, good. So this is the read and the write head. So there will be two kinds of heads, one for reading purpose, other for writing purpose. So I'm writing them as the RW head. Is the figure clear? So the figure on the right hand side that has been shown, which is an opened up hard disk, you are looking at only the top disk. Remember, there are layers of disk which are there. Okay? And this is the head that you are looking at. So that's as it rotates, it touches and the data is read. That's how data is read from the hard disk. Well, so how many typical heads can we have? We can have 2 to 30 heads. If you have only one single disk, you have 2 heads. Okay, so you can have platters, and there can be 2 platters. The diameter is typically of the order of 14 inches to 2.5. It can be different sizes of hard disk you have. There are about 700 to 20,480 tracks per disk. There are about 16 to 1600 sectors. Okay, this is what we have, and the sector size is of the order of about 64 to 8K. 8K to 64K, this is the typical range of the sector size. And minimum is 512. I've already told you, we have already seen one such sector, the boot sector, which is of size 512 bytes. And the capacity of hard disk typically of the order of from 20 megabytes to today 100 gig or maybe 1 terabytes or a few terabytes today. So that is the order of data that you have, or the number of bytes that you can store onto this particular hard disk. Okay, now how are these arranged? Very important. So the data that you are going to store is stored in the form of a sector, comma, track number.
Sir, what is platter into 2?
Platter is the disk, the top, the entire surface area of that particular disk. I'm referring to that's the platter.
So, sir, for each disk we would have 2 heads.
Yeah, I can have two heads. If you require, if you are having two, if you are storing data on both sides of the platter, then you will be requiring 2 heads, one for the top head, one for the bottom head. Okay. So what is the block of data? If you are looking at a hard disk, the block of data is usually given by a sector number and a track number. Okay. Why? Because let me show you the movement. How does this head? There are 2 movements that are involved. The disk will rotate on the spindle. It's like this. And the head will move in this way, right? So the head will move along the sector. Sorry, along the track. Okay? Because if this is track number 0, this is track number 1, track number 2, and head is moving laterally. So obviously it will move along a track. And the platter is rotating. So as it rotates, the sectors keep on changing. So that means you require information about the sector number and the track number if you are mentioning the corresponding block of data. Is that okay with everyone? The platter rotates, so the sectors change, and the head rotates laterally, so the tracks change. So to mention the block of data, you require the sector number and a track number. This is a tuple. 2 things you need to tell. Now, interestingly, what happens is these corresponding tracks. If you see the tracks, if they are arranged, and they are arranged in such a way that the tracks of different disks they form a cylinder. Look, the track number 0 of this disk, track number 0 of this disk, track number 0, they are aligned absolutely vertically so that they form a cylinder. Similarly, the track number 1s, they form a cylinder. Okay. Track number 2, they form a cylinder. So a block of data actually is a cylinder number, track sector number, and track number. So it's like this. You can assume cylinder number and sector number to be same, because after all, when you are mentioning the cylinder number, you are actually mentioning the same track number for all the disks. This is the way of mentioning a block of data for a hard disk. Is that clear, everyone? Okay. So what is the, yeah. So suppose you are in some track, okay? Suppose you are in some block, let me call it block number I, and you have to move to block number J. Got it? You are in block number I, you will be moving to block number J. So we should understand how will this movement take place and what exactly we need to provide. Cylinder number and track number works, and yes, absolutely, you're correct, because cylinder number is nothing but mention of the track number as a whole for all the disks. Now suppose there is a block number I, and the next block that you have to fetch is block number J. So your disk has to move, correct? Your block number I will be now move, your head should be below block number J. It was previously below block number I. Now there will be movement in the disk and your head should be below block number J, or should be above block number J. Now in order to move from block number I to block number J, there will be two kinds of movements: rotational motion, translational motion. Rotational motion of the disk, translation motion of the head. So block number I means cylinder number and track number to a new cylinder number, track number. Now because there are two kinds of motion, there will be two kinds of, and both these motions will lead to some amount of time being spent. So when you move from block number I to block number J, one of the motion that will take place is, so I'm removing that. So the motion that we would have is, one of them is called C. What is that? It's the movement of the disk. Sorry, movement of the disk arm. Okay, to what? To the right. Okay, so to the right track, because it will be moving in this way. The arm, it will be moving from one cylinder to the other. So the time spent in moving from one track or cylinder, sector or cylinder to the other is called seek time. So tell me, what is the best case seek time that you will have? What is the best case seek time? Best case seek time will be when the next block, that is block J, is also on the same cylinder. Absolutely. You are in block I, which is some cylinder and some sector, some track. Okay. Block J, if you are in the same cylinder, then basically you don't have any seek. So the best case is when you are on the same track. When you are on the same track, that's the best case. What is the best case time then? Obviously 0 milliseconds, no time spent. What is the worst case? What is the worst case? Worst case is you have to move from the outermost track to the innermost track, or from innermost track to the outermost track. Translation motion, absolutely, you are completely covering the diameter of that particular disk. If that is the movement, you are having the worst case. So in this case, it is like about say 30 to 50 milliseconds. Look at the amount of, the span of the best case and the worst case seek time. So the time spent in movement of the disk arm from one track to the other is the seek time, as you are moving from one record or one block to the another block. It may happen, right? Block I may be in the most innermost track, and the next block that you have to fetch is on the outermost track. In that case, you have the worst case movement of the disk arm. Okay, this is what we have. This is the first movement, seek time. What is the second one? Well, the second one is the rotational motion. So we have a rotational delay. And what is this rotational delay? It is the amount of time for the to rotate under the head. So your disk is rotating. You have to rotate it to come to bring that below that particular head. What is the best case in this case? In this situation, what is the best case? What is the best case? Yes. If disk arm movement is on track, what is the rotational motion? What are moving when the disks, what are changing? The sectors. What is the best case? The best case is, yes, you are over the same sector. Okay. In this case too, you will have your best case, which is 0 millisecond. And what is the worst case? Worst case is about 16 years. Worst case is you have whole rotation. So this is 16 milliseconds. So considering these two rotations, if I am moving from block number I to the next block I have to fetch is block number J of my hard disk, then the total time that I have to take, or the total time of my access, so let me call it as time of access, will be given by my seek time and my rotational latency. Both of them will add up to my total amount of time for my disk access, just from moving from one block to the other. Okay. And what you get is about something like just a single sector. I'm just giving you a typical order of a single sector. It's like 10 milliseconds plus 8 millisecond plus, let's say, the transfer time, that is the time spent in transfer of data, is about 50 microseconds, and it is of the order of about 18 milliseconds. Okay. So this is the basic idea. Now, in some cases, you see the seek time is the one that's more important rather than the rotational latency. Rotational latency is not important to me. To me, the important thing would be, more dominating part of this total time would be seek time. So the idea is, can we have some kind of mechanism by which we can control this seek time? This is the different algorithms that we are going to talk about today. Is it clear? So you see, from as you are moving from one block of data to another block of data, you are required to spend some time in the seek as well as in the rotation. For the time being, let's assume that seek time is the one that is more dominant. So what are the different algorithms that have been developed to reduce the seek time? Okay. So the first among them, as you see, has been written as SSTF. It stands for shortest seek time first. What is it? Can we have an algorithm by which we may decide that which are the blocks which should be accessed? Okay, so it's like this. Let me give you a basic idea. So the first one is I'll just show you the different algorithms, and then I'll give you an example to see. With an example, I'll show you how people have proposed different kinds of algorithms and how they have been improved gradually. Okay, so the first one that we are looking at is called the shortest seek time first. So as you see, the algorithm says that you know the head position, you know the current head position. Let me give you an example. Suppose my head positions are like this, that I am given that your file, to access that file, you have to access, let's say, block numbers 16, 20, 35, 15, 2, 8, 80, 88, 100, 12, and 22. These 10 blocks have to be accessed. So we just saw that how the hard disk operates. So you have to move from one block to the other to obtain that. So let's assume that this is the scale. We can just, and our current head is in position, let's say, let's assume it is 50. Your current head is just above block number 50. And these are the different blocks numbers that you have to access. Okay, this is what it says. Now, shortest seek time first. The first one before this, mentioning that, which is TS, and this is the most simplistic implementation of any schedule algorithm. It is kind of a scheduling because we are trying to schedule the block requests. So FCFS would say, okay, well, you have to access, you have to rotate and go there as the requests come. So if you are in 50, you will first go to 16. Okay, then from 16 you will go to 20. Then from 20 you will go to 35. From 35 you will come to 15. Okay, from 15 you will go to 2. From 2 you will go to 80. See, that's first come first. So what is the problem with this? The problem is too many disk movements. Why? You started with, in the first movement that you would have is from 50 to 16, 34. So number of head movements, if I count, the first one would be 34 as I move from 50 to 16. The next movement will be from 16 to 20, 4. Then I will move from 20 to 35, 15. Then I will move from 35 to 15, again 20. See how many disk movements I'm having. And every time you have so many movements, you will have the movement of the arm. And the more you have the movement of the arm, you will have a greater seek time. So I leave this as an exercise to you, and it's also provided in your textbook. Find out the total number of head movements that you will have if you go for first come, first serve scheduling algorithm. A lot of head movements. The more head movements, the more that will reduce the performance of your system. So what to do? Come up with a more innovative algorithm that would reduce this number of head movement. What does it say? It says you know your current head position. Yes, I know that. It's in 50. You try to find out the next IO that should be accessed, which is closest to the current head. Okay, only you know. So whenever you schedule the next one, you decide which of them is the closest. Okay. So you see, analogous to the shortest job first scheduling. Yes, absolutely. You decide. Look at the what did we do in case of SJF scheduling? We tried to find out the job with the minimum burst time, and we executed it first. That's exactly the idea. That you find out the head movements, the tracks which are closer to the current position, and you execute them or you access them first. Then you go for the ones which are distant. So in this case, you have to compute what is 50. From 50, you try to find out which one of them is the most closest. So say it's 35, maybe 15 is there. So you reach to 35 first of all. And from 35, you try to find out when you are in 35, look at the others who are there. It's like at 30, so from 50 to you first move to 35. And at 35, you decide whether I should move to look at which one is the closest. Is 16, 20, 15, 20 is the closest, or maybe 22 is the closest. So from 35, you go to 22. When at 22, you go to 20. When at 20, the next you go to 16 because all the rest of them are pretty far from 20. So what you're trying to do is you're trying to minimize the seek time by looking at the tracks which are closer. But there's a problem with this algorithm. The problem is that for the distant cylinders, they may get stuck. Yes, because you see, once you have moved to this part of the head, that is for heads which are lower than 50, you are always moving around the lower than 50 side. And the ones which are higher, let's say 80, 88, 100, they are not getting chance because the lower side cylinder numbers are frequently accessed. So this is a problem that the distant cylinders, they may get stuck. They may not get the access. So what is to be done? Well, to remove this particular problem, we move into something called the elevator algorithms. And this is the one that is frequently used. What is this elevator? You know what an elevator is? We normally call it the lift. How does it operate? It operates in this way. Suppose you have pressed an up or a down button on the lift. Now, if you are in let's say a fifth floor, and you want to go down, you press the button to go down. And now somebody in between, let's say at floor number 3, presses the button and presses button number 4. Okay, now think, that would eventually lead to a fight because I want to go down and the person who boarded the lift at floor number 3 wants to go up. Okay, so that would eventually cause a fight between both of us. The elevator does not work in that. Once I have pressed the lift and I am the one who pressed it first, whether you have boarded it from floor number 3 and want to go up, doesn't matter. You first have to go down, touch the last level because I wanted to go to floor number 0, and that is why I press the ground floor. Until the lift reaches ground floor, even if you press 4, it does not interrupt and does not go up. So depending on whatever I pressed, it will first complete the entire algorithm, go there, and then will take your request. So if you are a person applied or put a request, your request will be in queue. My request will be first served. The entire process will be done till my request gets served, and then your request will be served. This is the elevator algorithm. It works like a lift. So exactly this is the mechanism that we are going to prefer for scheduling these disk requests. What will happen? You will know the head position, and you will also know the direction. You know in which side am I moving. If you are in currently your head is at 50, you want to go to a head which is lower than 50. You will start scanning all the block requests until you reach to the last. So if you are currently your head is 50 and you have all these, which is like 16, 20, 2, 15 in this way. So you go on serving them until you reach to the last one. There is no other request is pending which is lower than 50. Once you have touched upon this, then you start traveling on the other side. Okay, from here, this. So this is how you're going to come. Look, you know the head position. Obviously, for all the scheduling algorithms, your current head position should be known. And you know the direction. In which direction should we travel? Should I travel from greater than my current head position or lower than my current head position? But once you have started, all the pending requests along your path should be executed. So you schedule the pending IO in the sequence of the current direction. If you are moving towards the lower than current head position path, all the requests along that path will be covered. When the head reaches the end, once you have reached to the last pending request, not necessarily to 0, the last pending request along this path, you reach there, now you switch direction. Now you start moving towards an increase of the pending request. Here you had moving. This is the basic algorithm. What if continuously? Yeah, that can be. So you are assuming that, but somewhere, even if you are constantly addressing the lower request, somewhere you will stop, isn't it? Somewhere that lower request will stop and you will change your direction. Now, elevator algorithms has different categories of elevator algorithms. There are different variants of that. The first one is called the loop algorithm, the loop elevator. So what do you do? Now, when there are no more blocks to read or write in the current direction, then you switch direction, the one that I told you. When you don't have any other directions or pending requests to be accessed, you change. Then circular scan. Now, this is an interesting one. It is like a scan. Scan means the standard scan, the standard elevator algorithm. But in circular, when you reach to the end, you see the beginning without servicing the eye. It's like this, that you just turn around. You reached here, okay, and then suddenly when you reach here, you don't move along this path, but you start scanning along this path. It's like you completely, you give a shift and you start from the other end. That's why it's called circular scan. Elevator what? Elevator takes one path, reaches to the bottom, and then from the bottom it starts moving upwards. But it's not like this. You reach to the top, and then as if you completely switch over and you start again from the other side. This is the circular scan. So that's again the variation of that. It says when you reach the end, you seek the beginning. You don't start from the other side, but you just rotate and you start again from the beginning. Okay, so this provides more uniform wait time. So I would suggest all of you to go through your textbook to have a more details about all these three algorithms, and there is a numerical problem that has been solved which shows how each of them perform. Take one example of a string of IO requests and try to apply the different algorithms on each one of them and see which one of them gives the minimum head movement. That's a numerical problem that is very commonly solved for this algorithm. Is the concept clear how the disk gets accessed? Anyone? Any problems regarding this? Is it clear? Okay. There are quite a few other scan algorithms as well. I'm not mentioning about that. So if you're okay with this, let's go back to the concept that we were discussing. I repeat, is the concept of IO or the block scheduling of hard disk clear to everyone? There are two more. Yeah, there are two more that is mentioned in the book. Please go through that and solve the numerical problem. It's very important, a very commonly asked question. Okay, so this is what we understood, right? That we have a device.
Sir,
yes.
What C-lock?
Pardon?
C-look, sir. C-look wasn't clear.
I mentioned it, isn't it? This is mentioned here. Okay. We know what look is. Look says when there are no more blocks to read or write in the current direction, you switch direction. But here it's circular loop. Previously it was circular scan. It was scanning and then you see to the beginning. It's the look algorithm with a circular effect in that. That is what was look doing? It was.
Sir, that's clear.
Yeah,
I'm asking about the third one, C-look.
That's what I'm saying. Look at the look algorithm. It says when there are no more blocks to read, you switch direction. But here you don't switch direction, you again go back to the beginning and start. Okay. There are two variants. One is scan and circular scan. Just go through the scan algorithm. When the head reaches the end, you switch the direction. Circular scan, when head reaches the end, you don't switch direction, you start from the beginning. Look, when there are no more blocks to read or write, then you switch direction. Scan means when you start, you start. You go till the end. Okay, let me show you the difference. Here you started at 50, right? There were some requests which are coming, 16, 15, etc. So scan says that once you started off moving in a particular direction, you go until you reach the end, which is 0. And then you start moving here. Look says, no, don't go to 0. Stop till the end, which is the currently servicing requests. So for look, it will be from 50 up to, let's say the last was 2. You go to 2 and then you switch direction. This is scan and this is look. C-scan is you come here from this up to 0 and don't switch direction from here. You start your next movement from the highest of this, which is, let's say, 100 in this case. And C-look says, no, you start from here, go till the last one, which is in this case 2, and when you reach here, you don't start from 100, start from the one which is highest from the request, which is, let's say, 80. So you start from 80 and you move along this. That's what C-look says. Is that clear to you?
Okay, sir, got it. Yes, sir.
Now, so this is what we understand, that devices. We took an example, typical example of a block device, and we found that you have to be intelligent enough to understand that how the device would be moving. Well, that movement of the device that we studied, that you move from one sector to the other in an intelligent way using any particular algorithm, has to be at the lowest level. Who does that? Who sends this information that this is the device, or where do you implement these IO scheduling algorithm? Where do you implement? Anyone? Where do you implement this IO scheduling algorithm? We mentioned all this yesterday. Where do you think this IO scheduling algorithm will be maintained? You will have a set of blocks that will be generated, right? By the way, who will generate this set of blocks? Your application wants a particular file. Okay, let's say you have written a text, some text editor, you wrote a file. Mantra says device driver. Yes, absolutely. So you have written a file, and that file was generated by some application, say for example a text editor, and you save that. The moment you write file save, that file or this array of bytes, they get stored in the hard disk. And you know that in hard disk we store it in the form of blocks. So your file of a certain size is equivalent to certain series of blocks. These series of blocks have to be stored. Okay. Who will do that? Who takes care of this? Who ensures that this series of blocks are stored on the hard disk? This is done by something called the device driver. So there is a lot of things which are involved. If I can group, I call it the IO subsystem, okay, and the device driver. So these two things, they take care of those low level happening that we just saw. So what is this IO subsystem? It's those modules of the computer system that interact or ensure communication between the computer and the IO device. So this is the one that makes sure. And this device driver is the piece of software that is present within the operating system that ensures that the application can, whatever the request the application has put, is passed on to the IO subsystem. So it behaves as an interface between the IO subsystem and the application or the operating system. So your application wants to access a particular file, but that file is stored in the hard disk in the form of some list of blocks. So translation of that array of bytes into this list of blocks is what is the responsibility of this IO or the device driver, which in turn is passed on to the IO subsystem, right? So that's what we discussed yesterday. So we'll talk about that quickly, and then we'll move on to the other side, that is the file system. What we studied in the last class is how do these devices interact, or what is this IO subsystem consisting of? We studied that every system, whatever it is, it consists of some, every device that you have. Overall, if you can summarize that how the devices talk to the CPU, there are three things which are involved. One is called the device controller. The device controller is the piece of hardware that allows the device to talk to the CPU. It allows the device to talk to the CPU. Okay. Often you find this as a chip that is associated with the device, usually embedded within the device. This is called the device controller. The second is called the host adapter. This host adapter is the one that allows the CPU to interact, okay, with the device. It's the other way around. We even have seen that. And finally, we have those communication lines which are called buses. So in the last class, we saw what happens, and just to show you, I'll quickly just a minute. Yeah, is it visible? Class? Okay. So this is what we saw in the last class, that how this is the modern system architecture. You may call it IO subsystem, whatever. So you see, this is a device. Okay, so this is a graphics device. The graphics device is connected to the CPU. But what I haven't mentioned is that every device has a graphics controller. So in between this is a graphics controller. Similarly, every device that you see here, some devices are directly connected to the CPU, like memory and graphics processors. Others are connected via a chip, IO chip. This is the host adapter in this. So that gets connected via the IO chip to the CPU. Now this is the connection. Okay, so the devices, they are connected. Whatever be the device that you want, it has to get connected to the CPU via some medium. It's called the bus. There are different categories of bus: PCI bus, memory interconnect, DMI bus, depending on the amount of data the bus can carry or how quickly the bus can transfer the data. Okay, coming back. What exactly or how does this communication happens? We already have seen in the last class. I'll just move on from here. We saw that if we can summarize what exactly happens inside any device, we found that the devices, whatever device you are talking about, they consist of some internal registers, so through which the device communication happens. So let me quickly recap. So what happened is, if you are talking about a particular device, let me say, suppose this is a monitor. So this monitor has to communicate with the CPU. Now, what will happen and how will this take place? Now, this is the monitor. This monitor will have something called, let's say, graphics controller. Okay, so we will call this as a hardware, which will be able to control this. And what do you have? You have a controller, some microprocessor inside, and there will be some set of registers. These are the ones which are most important. Out of that, one of them will be called status, second one will be called control, and then we'll have data. Then you may have some memory. Now, normally the hardware controllers don't have memory except for very high-end ones, like the graphics controllers, which have to perform some kind of computation, and they may require some memory. Now, this is what and how things work. And here is the different bus that is there. So this bus interface, they are connected to some bus that takes it to the CPU. This is how the communication is there. Okay. So the question is, how does a graphics controller, or for that matter, any hardware controller, communicate to the CPU? The rule says the CPU will program this controller. What do you mean by programming? It will perform some operation. What operation? It will check the status. How? There is a status bit here, status register. It will check the status register. It will put the command, and then there will be transfer of data. If you can summarize the entire operation, these are the three things that happen. The CPU checks the status, whether it is free or not, because this particular input or output device can be shared with others, so it may not be free. It checks the status, puts a command in the command register, and then transfers the data. This is the data that is actually written into this controller. And depending on the controller in which the data is written, the device works. Is this picture clear? We already have seen that yesterday. It was just, I thought that it's important to recap. Any questions regarding this? Is it clear? Read the status, put the command. What is the command? Read or write. Okay, and then you send the data. This is the operation that happens. So the data that you are going to write will be written in one of the registers of this controller. And depending on what data you have written, that will be passed on to the device, and the device will display that, or the device will provide the data. This is the mechanism. Well, you may ask, how does the CPU know about these registers? How does this happen? And that is where comes the concept of memory mapped I. What does it say? It says that all the registers of every device has an address associated with it. Okay? So I will call this as a memory mapped region. What is memory map? And this particular thing is having an address. Every register is having an address, and the idea is this. This is what we covered last class. The idea was that, let me quickly show you so that you get to know. Suppose this is the memory which the CPU is accessing. So the memory is divided into different portions, and these portions have been kept for separate devices. Suppose this is a display memory. Okay, this is a display memory, and it starts from 0x80010000, something like this. Then you have something as command, okay, status. You see, interestingly, when the CPU sends out a particular instruction for writing to a particular address, and the address that it is mentioning is not the address where your user programs run. They are special addresses. They are meant for devices. So any address which tries to write some data within this range will actually be writing something for the graphics. So whatever data you would like to print onto the display memory has to be written somewhere in this range of the address. Similarly, if you are looking at a particular device whose command register you want to access, it will be something like 0x0007F004. So any address that you will be, any data you will be writing to this particular address is some command register of a particular device. This is what we mean by memory mapped I. So all your registers of all the devices have a specific address, and if you want to write to that particular register, you treat that register as if a memory location, and you use the same instructions as you would have used for writing the addresses or for content in that particular register. This is what we studied in the last class, and this is what we called programmed I/O. Okay, so again, fine. So this was understood, but the problem is that during the process, when we were trying to access a particular device, we said that there are 3 steps: check the status, put the command, and then send the data. But when you are checking a status, it may so happen that the device is already busy and you don't get the device to be used. So what to do? So the process that is currently not having that particular this or not is called polling. So this when you check the status, there are 3 ways in which you can perform this operation. It's called polling. Or you can, maybe the other way around is you don't care about when the device has become ready or not. When the device will become ready, it will automatically send an information that ready. So that when you do not waste your time in unnecessarily checking, you do some other work. That is called an interrupt driven approach. And the third was a DMA, when there is a separate entity or a separate controller that takes care of the communication between the hard disk and the memory, because the data that you actually have to bring in has to be from the hard disk to the memory. Okay, so these are the things that we covered the last day, and we also went ahead to look at the piece of software which is part of the kernel that actually allows the interface between, or it acts as an interface between the application and the IO subsystem that establishes the relation. And that is where, and that is the software called the device driver. So on one side, the application puts a request for some device through some system calls, but these system calls are not directly meant for the device. They are translated into the translated into something that is understood by the device. So let me give you an idea that will make things clear to you. Now that we have discussed about the structure, let me put an example. Suppose I am using something called a disk controller. What is disk controller? The hardware that controls the movement of the hard disk. And now let's say I have mentioned something as a command which is like, I say access sector 23. This is the command that I have generated. Now there are a few commands before that. I'm not going into this. Let's say there's an application that wanted some file, and accordingly it put some open instruction, provided some open. This application wanted to open some file. Accordingly, there was a system call called open. This system called open has been translated into this low-level instruction, such as access sector 23, because the file that you want, let's say f1.txt, actually is block number 23, block number 25, block number 26. 3 blocks have to be accessed. So open system call is translated into access sector 23. And this access sector 23 in turn will be converted into something like move the head to say 1.67222 centimeters from the edge. Look how the higher level instructions are gradually being translated at every step into more sub level instructions, which are actually implemented by the IO subsystem. And this is the actual movement that is done, and this is what is taken care of by the disk controller. So these are the two instructions that basically the instruction that is executed by the disk controller is this one, and this is the one that the disk controller advertises to the operating system via the device driver. So the device driver gets that, and the device driver it hides the disk controller, it hides the details, and it gets as an input access sector 23. Okay, so this is, you see the interfaces that are provided, and these are all provided via the device drivers. Okay, what is the we just saw the device system, or what is the what does this device driver consist of? It consists of some IO scheduler that takes care of those scheduling algorithms of movement of the blocks, some generic device driver code. Device driver code is the one that acts as an interface that can understand or take those system calls as input and accordingly translate them into some form of the lower level instructions which is understood by the hardware controller. And they are drivers for specific devices, obviously, because they are specific to the device. We have already seen all this. We saw different modules and how they are maintained. We also introduced the concept of buffer cache. This is a technique by which you can reduce the number of accesses. How? We know that the number of blocks that have to be accessed, if they are the ones which are frequently accessed, you can keep some part of the primary memory to keep the block content there. Because every time you go to the hard disk and access those blocks, that will take a lot longer time. Rather, why not keep it within the primary memory? Because you know that these blocks will be accessed. So that part of the memory, which keeps the frequently accessed blocks, will be called the buffer cache. So whenever there's a request for some blocks of IO, the first thing that will be serviced or checked is the buffer cache. If those blocks are not found in the buffer cache, then you move to the device block request. Okay. So this is the basic idea of operating the lower level blocks. Okay. Blocking and non-blocking that we mentioned yesterday. This is the two ways in which you can work with the different IOs. One is where whenever there's a process that requests for a block, the process is put to sleep. Until the entire block is read from the hard disk, the process will not work. This is called blocking. The second one is non-blocking, where it immediately comes back from the read and it reads how many blocks have been read. That's called non-blocking. It does not wait for the output. It just provides the request and then it comes back saying that, oh, these many have to be read. But it constantly reads whether the transfer has been finished or not. That is why it polls. And asynchronous is you don't care about that. You simply come back and the system will take care of whenever it is finished, it will signal that, okay, the data has now arrived and you can proceed. This is the mechanism of the IO. I hope that is okay with everyone. This is the most lower level stuff that we should know, because until you know the lower level operations, you will not appreciate the higher level stuff. That is the next part that I'm going to start now. Is the concept clear to everyone? How the IOs are connected, how they interact with the device, how they are programmed, how you decide which blocks to be arranged. So now that you understand the structure of the devices, how the devices are connected to the CPU, now we will move one step above. And now the question is, okay, we understand that any store in a device is like a block, if you're talking about a block level device. But when we are working with an application, it's not a block, it's an array of bytes. So how does these two, how are they translated? That is what we are going to talk about now. And the way to do it is something called file system. So let's move towards the next topic, and we are going to talk about now the file system. Is it clear to everyone? Any questions so far? Should we proceed with the next topic? Okay. So what is file system? And before I move on to the file system, let me mention some terminologies, because it's very important to know these terms before we can proceed. So what is a file system? All of you are aware of what files are. Simplistically put, a file is an array of bytes. It contains what? Data that you generate while you are working with any application. Say, for example, you have opened a text editor and you have written something, any text document. So that's a file. Okay. So what is a file system? The file system it's a way to manage variable size persistent data. You know that the data that we generate is of different sizes, different type. So it has to be managed properly. Until you manage them, you cannot operate on the data. So there is a way to organize, store, retrieve, and delete this information. This is what we mean by operation. Okay, how are you going to store the data? How are you going to obtain the data? How are you going to delete some data? And for that, you have these mechanisms. One is random access. And please understand this very, very clearly because we will frequently be using these terms. So the first is random access. You want to access the files according to your own, you want to access them whenever you want. And there is no ordering. It's not that of one file will be accessed, then the next one, then the next one. No. The files have to be stored, and I can access any file at any point of time. So how will I arrange them so that I can do it? The second is I can arbitrarily access parts of a file. Yes. Suppose a file is split up into 2 to 3 parts. You may want to access any particular part of that. For example, you are storing some record. You don't want to access the entire record. You want to access only a part of that. Okay. You want to access only some part of a table. That's some part of the file. You don't want everything. So how can you organize the data so that you can access parts of that? So what should be done? Well, for doing that, you need something called file systems. So what are file systems? They are the ones that will help you in implementing or organizing your files. And they are implemented on top of block devices. So please try to understand. The files will ultimately be stored in the block device. Say, for example, your hard disk in the form of some blocks. But those blocks, on top of that, there will be an abstraction which will be seen by the application. The application will not see the blocks. It will see some, some kind of names. And this is what the file system is. Let's try to understand. File system is more abstract. It is not the actual position of the file. It is just a way to access the information. Which information? The information that you have stored on your hard disk through or by using some names. Where some devices, you may want to access the device. We just saw that one mechanism of accessing the device is through some files. Even devices are accessed through files. Or you want to access some information through some system configuration, some process info, or some random numbers. Okay, any mechanism you want to go with, you can. Let's look at. We have already seen what a hard disk is. It's a non-volatile block device which stores a lot of data, and each one of those blocks is identified by what you call, we are writing it as sector, but it's actually a tuple which consists of sectors and cylinders. So the smallest chunk of IO which is residing on the disk is called a sector. It can be from 512 bytes to 4K bytes. As you see, we have 4 TB drives now, which is so many bytes, so many sectors that we have. Okay. So gradually, I am defining one by one the different terms. Disk has a number of blocks. A disk has a number of partitions. Okay. What are these partitions? They are nothing but a set of contiguous blocks on a disk. Contiguous means one by one. So let's say you decide that some 1,000 blocks I will call as one partition. Okay. A disk should have at least one partition. So it has greater than one partitions. Now, when you format your disk, how many of you have formatted disk? Or you may have at least installed an operating system on your computer. How many of you have done that? Siddhant says yes. Anyone else? Have you installed your operating system? Only one? Okay. So when you install your operating system, have you seen when they ask you to, show when you try to, the moment you start, installing an OS, your partition manager, I mean, the tool that helps you in partitioning, it shows your entire disk and it shows you that, okay, you have 512 GB of your hard disk. How are you going to divide that entire disk? Now you say that, okay, I will keep maybe 100 GB for partition, or which will keep a certain style of data. The next 100 GB I will keep for different style of data. The next 100 GB I will keep for different style of data. This is how you do. So what you are actually doing is you are reserving certain blocks in your hard disk which will hold a particular type of data. And that is what you are calling as formatting your disk. Okay. So you decide that out of 512 GB of my hard disk, I will allocate some maybe 100 GB for holding a data which is of type NTFS. So you are reserving those amount of blocks. That's what we are calling as partition. The next thing is called volume. What is volume? Volume is a disk or disks that contains a file system. So when you are reserving those blocks, what are you going to put in that block? You're going to put certain kind of data within that block. Okay, you are going to arrange those files in a certain way, and that is what we call file system. So the disk that contains a file system is called a volume. Now, interestingly, volume is not necessarily within one disk. It may span across disks, maybe two disks. Okay, your entire file system is extended to two disks. It may happen. Keep this in mind. Okay, we have already seen track cylinders, so I'm just skipping that. These are the terms that we are going to see very frequently. What is file? It's a unit of data that is managed by the file system. Okay, the data that will actually be managed. Data is the content that you have put. Data can be of different type. It can be structured, which is record. Record means there will be a particular style of writing or keeping your data. That's called structured. Records, database, tables, all these are structured data. Unstructured is the normal files that you have. You keep on writing any multimedia file or whatever. They are just byte streams. They are just arrays of bytes that are coming. They are unstructured. So there can be different categories of files. Structured files, unstructured files. Name. What is the name? It's a textual name that identifies a file. So the file will be identified by a string of characters, and those string of characters are called file name. Okay. Now, in addition to the actual content of the file, which we call the data, every file has some metadata associated. What is metadata? Some additional information about the file. What is that? The additional information will be the creation time, the permission, the length, the location of the file data, etc. So these are the different information that you have. Okay. I think all of you have seen that whenever we want to see the details about a file, you click on the file, right click, and add the properties. So whenever you click on the properties of a file, that gives you the information about the entire file. That's what we call the metadata. Recall, same thing we had in case of a process. And now tell me where did the metadata of a process reside? Where was the metadata of a process residing? Siddhant says PCB, exactly. Very similar to this, the metadata of a file resides in something called inode. Okay, this is the one that you will encounter very often. So when we will be talking about files, we will always be referring to an inode. What is it? It is the data structure that holds the metadata of a particular file. How is it identified? It is identified by a number, which we call inode number. So the moment you create a file, an inode of that particular file is created. There's a number associated to that particular inode. So accessing a file invariably requires accessing the inode. That's the first thing that an operating system should do. So please try to remember all these terms, because these are the ones that we'll be using very frequently. Okay, fine. So once we know that file is nothing but some content that is generated by some user or some application. Every file has a metadata associated with that, which is stored in some data structure called inode that has a number associated to that. Now, every file has or will have an attribute. What is that? It's a form of a metadata. What is this? A textual name and an associated value. So you will have a name and associated values, which we call the attribute. For example, you have a source URL, the author of a document, the checksum. These are some additional information that you provide to the file. And last comes something called directory, or often we also call it folder. What is that? It's a container. Directory is also a file, okay, but it's a special file because it is a container that contains file names. Now, this is the difference between a normal data file and a directory. A data file has some user generated content, which can be structured or unstructured. But directory is a file that contains list of file names. Okay, what are they? They are not only file names, it can also have name of other directories. So let us say if I'm talking about a particular directory, the directory, if you are able to see the content of a directory, you will find that it has a lot of file names, as well as it also has names of other directories. Now, desktop is a directory which has other directories. Let's say a directory called student and a file called f1.txt. So if I see the content of this file called desktop, which is of type directory, I will see that it just contains a list. Okay, what does it contain? Later on, I'll give more details. If you look at this content of that, you will find the name, student, and the inode number of that. That's what it has. Okay, so it just contains the list of the files and the directories within that. Okay, so as you see that because it contains different directories, how do you arrange them? How do you arrange these directories? So they have a lot of ways to do that, and we call them as the naming style, directory naming style. The first naming style that was used was a single one. That is, you had only one directory. Suppose you have a directory by the name F1. So any file you create, you will have only one directory within it. So F1, if you have, this is, let me write it as a file will be represented by a circle and a directory will be represented by a square. So let's say there's a directory called A within which I have F1. So if I create a file F1, there will be a directory which is enclosed by that. Okay. Now every single file will have a single directory. This is the most naive way to have a naming of directories. What is the problem with this? The problem is that you will soon run out of names because you cannot share the directory among files. So every file will have a single directory. It's a flat structure. Okay. This is the first way. The second way is, okay, maybe I can have at max two F1 and F2. Okay, two of them. That's another way. Now, what is the problem with this? Again, you remove to some extent some restriction, but not so much. So you cannot share the file names. Okay, you cannot have two because there's only one directory. If you have that directory, because you have only one directory, and within that you have all possible files. So you cannot have the same file name, right? In this case, you may have, because you may have two layers, but the one that is commonly used is called a tree structure. What is a tree structure? It's like this. You start from a certain root, and within that you can create other directories. It is like, this is called the root. Within that you can have two directories, dev, opt, usr, home. Within that you can have a file name f1, and here also you can have a file name f1, no problem. So this is kind of a tree structure. Home can have multiple directories, let's say directory called student. Within that you can have files, desktop. Within that you can have files f1, f2. This can also have maybe s1 in this way. So this is another way of naming directories. Okay. So directories, which are holders of file names, can be arranged in different ways. One way to arrange this directory is a tree type of structure, as I have drawn here. Tree type is the one which starts from a root directory. What will be the content of the root directory? The root directory will contain information about its subdirectories, dev, opt, usr, home. It's like this. Root will contain information about dev, opt, home, their numbers, the inode numbers, some number here. This is root. Now they are directories. There is a distinguishing feature between whether it is a directory or a file. So by just scanning them, you will be able to know whether it is a directory or a file. Okay, fine. So if somebody accesses this particular root, and what I have written here is the inode of a root. So when this inode is accessed, you will scan and find, okay, here is something called home. What is home? Home is this inode. So from here you will jump to the inode of home. Okay, inode of home. What do you have in inode of home? Well, you have student and S1. So you have student and S1, and you have inodes of that. There's an inode number here, the inode number here. Which user you want to log in? Student. So that means you will be jumping to this inode. So this will take you to inode of student. Okay. What do you have in inode of student? Well, I have a directory called desktop. I have a file called f1, and each is having an inode number. look how I have arranged this entire thing as a list. And when your system will be accessing something, it will be jumping from one inode to the other. This is how I maintain a hierarchical structure of the different directories. So in order to access a file, there has to be a directory, there has to be a container. And the access will be first done on the container. The container will contain the list of that particular subdirectory file. If that file is there in that container, well, you simply go to the inode and there you will get information about that particular file. If it is within a directory, then you have to do one more scan, go to that subdirectory, go to the inode of that subdirectory, find whether the file is there. If it is there, fine. If not, again one more into the subdirectory in this field. This is called a tree type of arrangement of directory names. And this is the naming structure of the directory. Is this clear to everyone? Unix follows this kind of a structure. So the directory names are arranged in Unix following a tree type of structure. We usually call it single rooted tree, one root. Windows is a multi-rooted tree. It uses different kinds of hierarchical names. It has a separate name for the devices like C, D, E, which is different from the usual Unix way of naming the different directories. So I'll stop it here today, and in the next class I'll be working with, I'll introduce you to the different file system operations, and then we'll talk about different operations such as formatting, mounting, and we'll see different kind of validation, and then we'll move on to the different operations of files, and we'll look at the implementation of different files. Okay.